Catching you up to where we are now, we've implemented our sample and hold with the capacitor divider, and I have this jumper in place because I have changed this circuit here, and this is back to the way it was originally with the jumper on, and it has to do with this 510 ohm resistor right here in this circuit. So let's turn it on. Alright, so there's no AC coming in, so we're basically reading our zero value, and what we're reading is the when this switch is on, we get a current through here which charges this capacitor, and that was our error current basically, just by the way it's designed. And you can see that this reading is pretty high. It's, you know, a little over 1/10 of the full-scale reading of 1024. The program, by the way, the program I'm running, it reads the analog to digital converter and just displays the raw value. That's not the line voltage. That's just the raw value of the AD to converter. Everything was very stable until I added this jumper here, which connected those two circuits together. So this jumper connects this circuit up to our diode there. So watch what happens. I'm not going to plug it in. I'm just going to put this transformer down near my power strip on the floor. So you can see that the value has increased significantly. So it's picking up stray AC fields in the room here, which is why the reading jumps all around. I would say that's one of the ills of the circuit that we designed. It must be a high impedance circuit, and you don't get very stable counts. So let me take this jumper off. So we get less base current now, so our reading that we get that's kind of erroneous, this is going to be like a 0 point. We're going to have to subtract this value out of our final reading. So that's much lower now. So let's plug it in. We have some value near 280, and it goes up pretty high, and it comes back around 280, and it goes up pretty high again, and it comes back around 280, and it seems to cycle like that. And if you remember from our previous video, we said that this switch right here in our sample and hold is just the diode, and we had an AC waveform on the input, and we don't know the phase of the AC input. So in my program, I'm trying to keep time, and supposedly I'm making this reading once a second, but it appears that my timer is different from the power line timer, and usually the power line timer is correct. So what I believe is happening is slightly out of phase with the power line. So the 280 reading is the one we want, but when this switch remains closed, supposedly, when the power line is in such a phase that we're still conducting on that diode, then the reading goes way up, like right there. Then it comes back down. So what we got to do is find a way to get this reading in phase with the power line so we always get the right reading. So we're going to work on that. This is a quick update of where we are with this project. We have the capacitor divider sample and hold working. This is like the raw reading out of the A to D converter. You can see that the numbers jump around quite a bit. Hey, our second helper. Numbers jump around quite a bit. I think that's pretty much as good as we're going to get that. It seems to be very sensitive to hand capacitance, sensitive to picking up stray AC fields. You're wiggling the camera, Gigi. So we have a routine that converts the raw number to the voltage on the line. You can see that that jumps around a little bit. That jumps around a little bit. And the blink over here is a routine we wrote to sync up to the line, sync up to the line phase. So we're sampling at say 0 degrees, 120 degrees, and 240 degrees on the AC waveform. And whenever we detect that it might be getting out of phase, we change a counter by 1 step to get it back into phase. So from here, we've got to detect conditions on the line that we want to save to EEPROM, and we have to write some EEPROM routines to read and write data. So we'll be working on that.